Hey guys, welcome to Unit 8, Note C. We're going to start the third section of the notes where we're going to look at partial dissociation of acids and bases. You probably didn't realize it at the time, but all of the pH and pOH calculations that we did in Honors Chem were based on strong acids and strong bases, which remember means that they 100% dissociated. And so we can assume that the concentration of the compound would be the same as the concentration of the H plus concentration, or OH concentration, assuming that that's a 1-to-1 mole ratio. We're going to look at that in a little more detail now and figure out what to do if it's not quite a 100% dissociation. First, let's look at an honors type question from a new perspective. Here we want to find the pH, and we're given the concentration of the base. And so what we've always done is assume that the concentration of the OH is equal to the concentration of the compound itself. Well, why is that actually valid? If you look at the balanced equation for the dissociation of sodium hydroxide, it's going to break down into 1 mole of sodium and 1 mole of hydroxide, meaning I have a 1-to-1 mole ratio of sodium hydroxide versus the hydroxide ion. That 1-to-1 mole ratio essentially means our concentrations are going to be equal. The concentration of sodium hydroxide can be converted into the exact same concentration of hydroxide ions themselves. So for this reason, we're able to treat this 0.1 molar as the concentration of the hydroxide itself. This is an assumption we did make in honors, we just weren't very explicit about it. We can also prove this to be true using stoichiometry. With a 1-to-1 mole ratio, the concentration of sodium hydroxide is equal to the concentration of the hydroxide itself. Now that we know the hydroxide concentration, we can plug that in and find the pOH. So finding the negative log of 0.1 gives 1 for the pOH. As far as significant figures go, the significant figures of the concentration, 2, become the decimal places for the answer, the pOH in this case, so that's 1.00. The thing is, we still really haven't found the pH, so be very careful when you're working with hydroxide concentrations that you understand when you do the negative log, you get the pOH. To find the pH, we need the complement of 14. So the difference of 1 from 14 is 13. Don't let that exact-ish 14 limit your significant figures. You're going to have the same decimal places for the pH and the pOH. So it's 1.00 for the pOH, leaving the pH to be 13.00. A pretty basic solution. Next, let's look at an example with a strong acid. So nitric acid is one of our 6 strong acids, and it will completely dissociate. And so we're going to get a 1-to-1 mole ratio of the nitric acid and the hydrogen ion or hydronium ion concentration. So with that 1-to-1 mole ratio, we can assume that the concentration given here for the acid is also the concentration for the hydrogen ions themselves. Once we know the H plus concentration, we can plug that directly into the pH concentration and we're able to solve directly for the pH. And the negative log of 0.15 is 0.82. So that would be our final answer for the pH. No need to find the complement of 14 because this time we were given the hydrogen concentration in the first place. So now you see the reason why I really emphasized memorizing your strong acids and strong bases. They make things so much easier when you can assume that 100% of the reactant turns into 100% of the product at a 1-to-1 mole ratio. Being able to assume that concentration is pivotal in saving time, but unfortunately, it's very rare. Most things are weak acids or weak bases. So what do we do for the rest of it? Well, when something is a weak acid or a weak base, that implies that it has a very poor ionic character, and that's why it's not dissociating very good. So that stronger covalent character is going to pull the equilibrium towards the left. It's going to indicate that the reaction is favoring those reactants because they're very bad at dissociating. But the quantification of how good or how bad something is dissociating really needs to be known in order for us to calculate what the actual pH or pOH or level of dissociation, the concentration of ions, pretty much anything we need to know about these reactions, we need to know quantifiably how much they are dissociating. So they call that the extent of dissociation. So they'll tell you, oh, it's dissociating 95%. Oh, that's pretty good. 5%. Oh, that's really bad. So we want to know how much it's dissociating. The higher the level of dissociation, the stronger the acid or base it would be. But the term strong acid or strong base is reserved specifically for 100% dissociation. But we need to know that number for any acid or base. The extent of the dissociation can be characterized by the equilibrium constant. And that's because this constant essentially gives us the ratio of products to reactants. And so we're able to see whether the reaction is favoring the right, which would be a high level of dissociation, or the left, which would be a low level of dissociation, based on whether the K is high or low. A high K would indicate a high concentration of reactants, whereas a low K would indicate a lower concentration of reactants. Think about the proportion here. So this is essentially what you get when you just simply do product over reactant, the simple equilibrium constant expression. But we can be a little more specific than that, and there's a couple tweaks we can do. The Kc just stands for the equilibrium expression for concentration, C for concentration. But this is specific to an acid dissociation, so we can actually call it Ka. The other thing is we have a pure liquid here. Remember that pure liquids do not appear in equilibrium expression, so we can get rid of that. So we have our new Ka formula for the concentration of whatever the conjugate base of the acid is, which will be some form of an anion, times the hydronium concentration over the original acid. So that would have a hydrogen attached to the anion, and then we factor out the water. So this is our finished, polished equation for Ka. A couple notes about Ka. Just like any other equilibrium constant, it is temperature dependent, so it will be specific to a specific temperature. And then also, it's going to give us an idea of the strength of the acid. And that's because K is basically constant for any dissociation. So regardless of the initial concentrations, that K is going to be specific to that dissociation. Regardless of what the initial concentrations are, we're going to get the same K. So as we look at the K for a dissociation, we can start developing a pattern of its strength. The higher the value for the K, the greater the dissociation. Keep in mind that K is basically product over reactant. The product is the ions. So the more ions we have, the larger the K, and that's consistent with the shift to the right, indicating a greater dissociation. So higher K, higher dissociation, and vice versa. A lower K would indicate a low level of products, which would favor the reactants and have a low level of dissociation. And again, because the K is a constant for the dissociation itself, it is not going to be affected by the presence of other ions. It is a constant. It should be no surprise that if you have a Ka, well, we probably have a Kb. So if a base reacts with water, we form its conjugate acid, and then of course the conjugate base of water. Keeping the water out of the equilibrium expression, we can then write the Kb equilibrium expression. You have your products over the one reactant of the base. So this is our equation for Kb. And hopefully it goes without saying that it would also be temperature dependent and constant. Now for the fun part. Since the Ka and Kb expressions basically characterize the degree of dissociation, we're going to use those in combination with Icebox and the pH and pOH calculations in order to be able to determine our concentrations at equilibrium. Before we get into the nitty-gritty, I'm going to go over a few identification things that's going to help us when we deal with the numbers. Before I do though, these are not things you would state as assumptions. They're simply how the problems work. So, when they give you the concentration of an acid or base, they're saying this is what is initially put into the flask or the system. That's what we're starting with. So at the concentration that you're given, that's the I for the ice box. It is before the dissociation occurs. However, when they give you the pH or the pOH, we assume that that solution's been sitting long enough to reach equilibrium. So the pH or pOH, whatever they give you, is going to be the equilibrium. So if you use your pH calculation, for example, that would give you the hydrogen ion concentration at equilibrium, not the initial. The next one is hopefully obvious. When you're using equilibrium expressions, use concentrations at equilibrium. That's what the K expressions are for. And then, of course, we have this assumption, and this one actually does need to be stated if you use it, that if we have a very small Ka or Kb, then we can assume the initial concentration is equal to the equilibrium concentration. In other words, you can assume X is negligible if you have a very small equilibrium constant. We're going to go over, though, the 5% rule. Finally. Now let's put it all together. To solve these questions, we need to be able to use equilibrium expressions, icebox, and pH calculations. I'm going to go ahead and set up the icebox as kind of a starting point, and then we'll figure out what we need to do to fill it in. What they give us is the initial concentration. Remember, we're assuming this is before dissociation of the ethanoic acid. So that's going to be our I for the reactants, and we assume there's no product yet because we're just getting started. No dissociation. Quick side note before we go much further. Yes, this reaction is in water, and yes, you actually form hydronium, but to simplify things, the water doesn't have a role in the Ka expression anyway, and the hydrogen ion concentration is the same as the hydronium concentration. So we really don't make a point of drawing that out. We can basically solve for the hydrogen concentration and be fine. Now we fill in the change. It's a 1-to-1 mole ratio, so it's X across the board, with reactants decreasing and products increasing. It might be tempting to assume we really don't know much about the equilibrium concentrations because they aren't given, but they gave us the pH value, and the pH is given at equilibrium. So from pH, we can actually find our hydrogen ion concentration at equilibrium. So using our pH calculations, we can find the hydrogen ion concentration as the antilog of negative 3.40, which is 4.0 times 10 to the negative fourth in its concentration, so that's in molarity. Then using the 0 plus x equals that number, of course x equals the 4.0 times 10 to the negative fourth, allowing us to also solve for the equilibrium concentrations of both the acetate, which is the 4.0 times 10 to the negative fourth as well, and the acetic acid, or I guess they've called it ethanoic acid, same thing, 9.6 times 10 to the negative third for that concentration, 0.01 minus x. Now that we have our equilibrium concentrations, we can start setting up the Ka expression. And that, of course, will have our products, the ions on top, and the acetic acid in the first place on the bottom. Once we finally plug in the concentrations at equilibrium for each of these substances, we can solve for our Ka of 1.7 times 10 to the negative fifth. And that is our final answer. Next, we're going to look at the calculation of Kb for a weak base. Now, on the last one, we didn't really bother writing the water because it wasn't super important because hydrogen and hydronium are the same thing. But without the water, we can't really get hydroxide. So typically you will see the water written, but we're not going to really include it in the icebox because it's not part of the equilibrium expression. We just wouldn't want to make it seem like we are violating law of conservation of mass when we make the hydroxide. So now we're going to set up our icebox ignoring the water, but putting in our concentration where we're given initially the concentration of the weak base. So we plug that in and we assume the products are 0 because this is prior to dissociation. Now we want to figure out the change, and it's a 1-to-1 mole ratio. So again, across the board it's just X where the reactants are decreasing and the products are increasing. Now we want to try to use what the pH is given as in order to find some information about equilibria. So the first problem is that it gives us pH, but we're interested in hydroxide concentrations. And those two things do not have a direct relationship. So the first thing I would do is take the pH and flip it into, take the pH and flip it into the pOH by finding the complement to 14. So we can see the pOH is 2.20. Now we can use that to find hydroxide concentration. So the hydroxide concentration will be the antilog of negative 2.20. With 2 decimal places, that becomes 2 significant figures. So that's going to be 6.3 times 10 to the negative third. And you can see that obviously would be x, since 0 plus x equals this number, x equals this number. So that also gives us our other concentrations, which are 9.4 times 10 to the negative second for our reactant, and both products being 6.3 times 10 to the negative third. Now that we have the equilibrium concentrations, we can plug that into the formula for the equilibrium constant. And that will give us our final Kb of 4.2 times 10 to the negative fourth, final answer. Now we're going to move on to a harder example. The harder questions will give you the Ka, and you need to work backwards to solve for our concentrations, allowing them to be plugged into the equilibrium expression as factors of x. There's a very handy assumption we used to make all the time, where if we have a small k, then we can assume that the change of the initial concentration of our reactants is negligible. Now I want to get into what happens if that's not going to work. So this is kind of going to be an ugly example in terms of like messy math, but it's a good way to explain our 5% rule that we've mentioned before. So for this example, we're given the pH of 0.1, we're given the Ka, and we're asked to solve for our pH. So we're going to start with the equilibrium expression. So with the nitrous acid dissociating into the nitrous ion and the hydrogen ion, we can write the Ka expression. And yes, you would have water and actually hydronium instead of hydrogen, but as we said before, we're just going to kind of leave that out because it doesn't really matter. So this is our Ka expression to get us started. Now we'll ease into this by setting up the ice box, which looks normal at first. The initial concentration given is for the nitrous acid, our reactant, and we assume there's no product made at first. The change is also normal. Everything's a 1-to-1 mole ratio, so we're just dealing with x with a decrease on reactants and an increase in products. So then when we kind of write the equilibrium expressions, we keep them in factors of x when we're trying to use the Ka. So these are our concentrations now at equilibrium as factors of x. Where we usually go from here is to assume that the minus x on the reactant is negligible and then plug that into the Ka expression to lead to some simpler math. Next, we'll use our equilibrium expression, the Ka, which is going to be our products, the ions over the reactant, the initial acid. Keep in mind we're leaving off the water and we're considering hydrogen ion to be equal to hydronium ion. So if we plug in the Ka, which was given at the 4 times 10 to the negative fourth on the left, and then we plug in our concentrations as the E or equilibrium concentrations from our ice box, both the nitrous ion and the hydrogen ion were x, so we have x squared up top. And then for the nitrous acid, we're assuming the x is negligible for the moment, and so that's just 0.1. So if you solve for x here, you get 6.3 times 10 to the negative third. Keep in mind that we assumed x was equal to the hydrogen ion concentration, so this is also our hydrogen ion concentration. So 6.3 times 10 to the negative third is what we're getting for that hydrogen ion concentration, which should allow us to lead to the pH. But this time we're actually going to check the 5% rule. The 5% rule kind of reminds me of percent uncertainty. We want to see that the X, in comparison to the initial concentration, which we were given here as 0.1, that percentage is less than 5%. So let's see what it is for this one. So if I compare 6.3 times 10 to the negative third to the original 0.1 molar solution, find that percent, we get 6.3%, which is greater than 5%, not less than. And so we should not use this assumption. This is a big no. It's not okay to assume. So what do you do when it doesn't check out? Well, that means you can't neglect that minus x, which means you have to plug it in with the minus x, which more often than not, actually almost all the time, pretty much leads to having to use the quadratic formula. So in case you've forgotten it, here it is. X equals minus b plus or minus the square root of b squared minus 4ac all over 2a. So we need to plug in our equilibrium expression components with all the factors, including the 0.1 minus x for our nitrous acid. So our equilibrium expression puts the ions over the nitrous acid, plugging in Ka on the left and our components from the E in the icebox row. This is basically what we've got. And now we need to solve for x using the quadratic formula. So we need to do a little bit of moving around to get this all equal to 0 so we can identify A, B, and C. So first multiply 0.1 minus x by both sides to get it out of the bottom. Then distribute the 4.0 times 10 to the negative fourth by multiplying it by both the 0.1 and the x. Then we subtract x squared from both sides. Now we're equal to 0. We can make this a little bit nicer sign-wise by basically like multiplying or dividing whatever by negative 1. And so we get the negative sign on the individual component that's not part of x. Oops, I keep leaving off x. And then the other thing is kind of writing this backwards would help, because a is the coefficient of x squared, and b is the coefficient of just x, and then c is the number without x. So here we have a little bit of a more polished version ready for our quadratic formula, where we have a equal to 1, b equal to 4 times 10 to the negative fourth, and c equal to 4 times 10 to the negative fifth. So we'll plug these into the quadratic and find our x. So here we can see everything all plugged in. The one little thing I wanted to comment on with the quadratic formula is there is a plus or minus sign, but there's only one answer. One's going to give you a positive answer and one's going to give you a negative answer. In this case, they are close. There's a negative 6.5 times 10 to the negative third and a positive 6.1 times 10 to the negative third. So you pick the positive one because you can't have a negative concentration. So the positive is 6.1 times 10 to the negative third molarity, or here it is, all with our IB units and everything. Final answer with using the quadratic formula instead of assuming that you can neglect x. I know that was so much work, but we still have one last step. We found our concentration, the valid concentration accounting for x, but we still haven't actually found the pH, which was the point of the question. So now that we have the correct hydrogen ion concentration, we can plug that in and find our pH. So plugging in 6.1 times 10 to the negative third as our concentration, we get a pH of 2.21. Notice the two significant figures becomes 2 decimal places. I know, nobody loves the quadratic formula. We don't enjoy using it, we know how to use it, but it is very tedious and time consuming. So I have good news. It's okay to not do it. You are always going to be safe saying that you made the assumption that the Ka is small, but you have to say it. You do have to state specifically that is an assumption you are making whenever you factor out that X from the reactants. But they're always going to be okay with you making that assumption because this is a time test. So they're not expecting you to go into the quadratic formula. I did want to do one example kind of showing you what to do in this case. You will see it again, I'm sure, if you pursue chemistry in college. But for your IB test itself, you don't have to do the greater than 5% method. Yay! So let's do some little examples where we are okay to make that assumption. So in this example, we're looking at the acetic acid dissociation again, and we have a pH, we're looking for the pH, and we're given the concentration of the acid in the first place, and we're given the Ka, so this tells me I'm going to be looking for equilibrium expressions in terms of X. We can plug in the initial concentration that was given for our acid and assume the products are 0 to start with. And with the 1-to-1 mole ratio, we have minus X for the reactants and plus X for the products. Then as we come up with our equilibrium expressions, we have 0.75 minus X for our reactant, and we can assume that X is negligible with respect to 0.75 because the Ka is small with a negative 5 exponent. Nothing is negligible in comparison to 0, so for our products, we just have X for each of them. Next, we'll plug in our E row for our equilibrium expression, allowing Ka to be given. The equilibrium expression has the products, the ions on top, and the acid itself on bottom. Next, we'll plug in the Ka, 1.8 times 10 to the negative fifth on the left. Both ions are X, so multiplied together, that becomes X squared. And on the bottom, we are simply using 0.75, assuming X is negligible. Now we want to solve for X. So multiplying 1.8 times 10 to the negative fifth by 0.75, and then finding the square root to isolate X, we get 0.0037. And so that is X, which we can see in our icebox table, literally is the concentration for the hydrogen ion. So that's going to make it really easy to solve for the pH, because I get to use X as the concentration of H+. So plugging that into the pH formula, I can get a pH of 2.43. The two significant figures from the concentration become 2 decimal places for the pH. Just for good measure, a little extra practice, let's look at the 5% rule. If I look at X in relation to the original 0.75 concentration, that is only at 0.5%, way less than 5%, perfectly acceptable to assume that X is negligible. Last example here using Kb. Again, we're going to be able to make that assumption that the Kb is small. So first we'll look at plugging in our initial concentration. So we know that for ammonia it's 0.2, that water isn't going to be included in the equilibrium expression, and for the products we start off with 0. Now we'll plug in the change with these 1-to-1 mole ratios. So that's just going to be negative X for our reactants and positive X for our products. Now we'll write E's with the components of X. So for the E, we have 0.2 minus X for the ammonia, but if we assume that the X is negligible since the K is small, then we can just simplify that to 0.2, and then for the products we just have X. So these are going to be what's plugged into our Kb expression. The expression itself will of course have products over reactants, or our ions over the original base. Now we're going to plug in the values for E. So we plug in again 1.8 times 10 to the negative fifth, the K this time for the base on the left, and then each of the ions are X, so we have X squared on top divided by 0.2 since we're neglecting the X. Now we just need to solve for X. So we get 0.0019 or 1.9 times 10 to the negative third for X, which is going to be equal to our hydroxide ion concentration. So on this one, when we're starting from Kb, there is going to be one kind of extra step here because we want pH, which does not directly tie to OH. So we have to figure out how to kind of work together with a couple formulas to go from one point to the other. First thing I would do is plug in the concentration to the pOH formula and get the pOH of 2.72, and then it's one quick step to get to the complement of 14. So 14 minus 2.72 is 11.28. Notice that the concentrations both have two significant figures, and then we go from two significant figures to two decimal places, which is true for both the pH and the pOH. So that's how our sig fig rules work. Alright guys, that's going to do it for Unit 8, Notes C1. In Notes C2, we're going to look at something brand new called the pKa and the pKb. We'll see you there.